Starting 5.5, we finally come to the algebra section. Really, 5.1 to 5.4 was sort of like the how to add, subtract, multiply, divide sort of thing. Those are just the operations. But again, in algebra, we're trying to get to the point of solving equations, trying to figure out what we don't know, set up the equation, and solve for what we don't know. Just a quick example with equations, since we're starting with equations now. Let's say we have an expression like this. So x over 2 minus 3 is equal to 2 over 3. How do we solve this here? The first step would be to multiply through by common denominator, something we've learned already before. And this is actually a problem from chapter 1. We'll see the difference why we start chapter 5 sort of problems here. So this is an easy one, just to sort of refresh our memory here. We look at trying to figure out what a common denominator is, multiply through by common denominator. You can multiply the same number on both sides. Remember, that's the multiplication property of equality. Remember that? I can multiply the same number on both sides, still keep it the same. But what we really want to do is we want to multiply through every single term by that number, because it's a lot easier to think about it that way. Multiply through by every single term. And if you need to cancel stuff, reduce stuff, you got it. You want to eventually get to this right here. Because once you get rid of all your fractions, it becomes a much easier problem to deal with. You do the operations for equations and you're done. Good. So multiply through common denominator, simplify, your denominator should be gone by then, and then finish off the equation. So go for it for number 1. Of course, we are going to get more sophisticated here. So look at this problem here. Let's see, common denominator would be 6. So instead of multiplying both sides by 6, what I'm going to really do, I'm going to multiply each individual term by 6. So everything gets multiplied by 6, and both sides get multiplied by 6. Alright, as planned here, that means some things will reduce here, so 3 goes into 6 twice. That's the whole point here, is to get rid of your denominators. If your denominators don't cancel all the way, that means you did something wrong. So 2 times x on top. 6 times 1, there's no denominator, nothing to reduce by, so it's just a whole entire 6 times the 1, gives you 6. And this side, let's see, half of 6 is 3, or again, changing both of them into fractions here, and reducing as much as we can gives us the 3. Alright, from here, how about subtract 6 from both sides? That leaves us the 2x by itself, but gives us a negative 3 on the other side, divide by 2, and eventually we are done. How about a negative 3 halves, and bless you. Okay, is it that easy all the time? No. Alright. What we do when we start really chapter 5 sort of problems is we're going to have variables, but those variables will be on the bottom. That's what we've got to think about here. So problem number 2 sort of starts off in this direction. Alright, so the next thing to think about here, before we start solving the problem, this is what we've got to think about. Remember, what's the only number we cannot divide by?
0.
Can't divide by 0, right? Remember we had this whole domain restriction in 5.1? So as I look at this equation here, what's the only number that will not work? What's the only number that will make this whole entire equation undefined? Let's see. My variable is here. So there's no variable here, so that's no problem. But right here, what would I plug into A? And if I add 5 to it, it would cause me a 2 over 0. 0 would still work, right? If you plug in a 0 into here, 0 plus 5 would be 2/5. That's still okay. And so this whole concept in 5.1, remember that little domain concept? Domain says x plus 5 cannot be equal to 0. When is it equal to 0? Is when a is negative 5, therefore a cannot be equal to negative 5. So everybody good there. Here's my domain restriction. So if I do all this work, and I get down to the end, and I get a is equal to -5, I can't use that number. That number will cause an undefined term to exist in the original problem. That was the whole point of 5.1, right? Can't divide by 0 from pre-algebra. Therefore, -5 causes the 0 here. Therefore, I can't use the -5. All right, the other thing that number 2 particularly has is this whole concept. Notice this is a proportion. There's two fractions that are equal to each other. And this one's just a shortcut way of doing it. If you see two fractions equal to each other, something from pre-algebra, remember something called cross-multiplying. I can multiply the, sorry, I'm going to back up. I didn't want to say that. Start it all over again. I'll give you the shortcut later. I'll give you the long way now. What is the common denominator? The a minus 5 is the common denominator, right? As well as the 3. So it's this and this. I'm sorry, a plus 5. A plus 5 and the 3. So let's multiply both sides by 3 times a plus 5 times the whole entire left-hand side. Then we're going to multiply 3 times a plus 5 times the whole entire, sorry, left-hand side and then right-hand side. Alright, something has to cancel, is that right? So on the left-hand side, how about the a plus 5s cancel? Leftovers would be 6 on the left, perfect. On the right-hand side, 3's are gone, and the a plus 5 times 1 is just a plus 5. And at that point, subtract 1 from both sides, and how about a is equal to 1? Can I use 1 as an answer? Yeah, I can use 1. I can't use -5. So cool. So we say a equals 1 is actually the answer to this problem here. Question?
Okay, so since you showed us the domain, every time we see proportion like that, we always have to look at the domain.
Good questions. When do we look at that? We look at whenever we see a variable in our denominators. That's when we look at domain. So for example, number 1, we didn't have to think about that at all, because notice there are no variables in your denominator. All the variables were on top. And I can have zeros on top, that's fine. But I can't have zeros on the bottom, that's not fine. So whenever you have variables in your denominator, that's when you got to think about it.
So the next one, that'll qualify since x plus 1.
Mm-hmm. Alright, what's the other mention? Oh, the other thing I want to mention about number 2 before we move on is whenever you see this little circumstance right here where you have two fractions equal to each other and nothing else, you guys remember something called cross multiply? So notice over here, 2 times 3 is 6. A plus 5 times 1 is a plus 5. So we could have went from here down to here right away without this extra step. Again, only works when you just have only two fractions equal to each other, nothing else. We won't see that a lot. Alright, this one. So, first question is, do we have variables in our denominator? Yes. So then what can x not be? X cannot be -1, because -1 plugged into that would give me a 0. And a -1 plugged into that would give me also 0. And we don't really care about this 2 because it doesn't have a variable here. Okay, next. What is my common denominator? Yep, the x plus 1 and the 2. Those are my common denominators. So I'm going to multiply both sides, or I'm going to multiply every single term. So 2 times x plus 1 times the first term. Put a little minus sign there. 2 times x plus 1 times the second term. And 2 times x plus 1 times the term on the other side of the equation. And again, can some of you guys do this in your head? Yes. Alright, the only thing you gotta be careful for if you're gonna do this in your head is in the first term x plus 1's cancel, so 2 times x is 2x. This is the problem area right here. Notice you got a little subtraction sign right here. This subtraction is subtracting this whole entire term right here, right? So when the 2's cancel, kind of careful, very careful here, you're really subtracting the quantity of x plus 1. Cool, so this little negative still has to sort of distribute over to here. So that's probably going to be the biggest problem on the exam right there. For these type of problems here. Don't just drop the parenthesis, because you still have the little x plus 1, but the x plus 1 is being subtracted from 2x. Okay, this one, x plus 1's cancel, 2 times negative 1 is negative 2. And the rest is all yours to finish off.
So that would distribute the negative 1 to the times x, and then negative 1 times negative plus 1, right?
So negative goes to the x, makes negative x, sorry, and negative goes to the plus 1, so makes a minus 1 as it distributes. Alright, gathering together like terms gives you an x minus 1 on the left. Adding 1 to both sides gives you that x equals negative 1. Uh-oh. Got ourselves some problems here. Computationally, x equals negative 1 is the answer, but as we go back to the original problem, that doesn't make sense, right? Can't use negative 1. Therefore, we cross it out. There are no other numbers here at all, so the answer is undefined. If I did have another answer, let's say factored down, I had two answers, x equals negative 1, and maybe like x equals 7, then x equals 7 would be the only answer. Alright, getting a little more sophisticated, more complicated here. If this was bad. Alright, see if you guys can stay ahead of me though. Let me jump to the next one here. I'll give you a little hint here. Something about, in order to even figure out our domain or our common denominator, you have to put everything into its factored form. So before we do anything else, let's put everything into its factored form. Alright, in factored form, hopefully the first fraction you got x plus 3x minus 3. The second fraction does not need to be factored because it's already in factored form, and the third fraction, factoring out the 4, gives you x minus 3 as the remaining part. So my question to you is, what's my domain? Well, from the first fraction, I go over here, would negative 3 be a problem right here, right? Negative 3 is a problem here. Positive 3 would be the problem here. So let's write negative 3 and then a positive 3. Just separate them by commas here. This one, hey, negative 3 is the problem here, but I already have that, so that's all taken care of. And then over here, positive 3 is the problem, but I already have it taken care of right here. Okay, good. So domain is taken care of. Now let's do the multiplying by the common denominator. Again, this is probably the biggest step here. Anybody? What is the common denominator? Oof. Okay, x plus 3, x minus 3, there's something else. That little 4 over here. And we usually like to write the coefficient first. So 4 out in front, x plus 3, x minus 3 multiplying the first fraction. And then we've got 4 times x plus 3, x minus 3 multiplying the second fraction. And 4 times x plus 3, x minus 3 multiplying the fraction on the other side. And notice I'm still using the factored form because that's the easiest one to just sort of cancel off common factors. Alright, let you guys try it first. Alright, and again, let me start canceling things here. So x plus 3, x minus 3 both cancel, left with the 4x. Careful here with this little minus sign again. There's your minus sign. So x plus 3's are gone. But you still have that negative 4 times x minus 3. So don't forget the little negative is going to be distributed here. On the other side of the equal sign, the 4's are gone, the x minus 3's are gone. So x plus 3 times 1 will just give you x plus 3. And check and make sure you guys got that right. If yes, keep on simplifying. Let me rewrite the problem here so I can finish it off here. So distributing the negative 4 gives you negative 4x plus 12. I like that. On the left hand side, the 4x and minus 4x cancel themselves out completely, so just left with a 12. Subtracting 3 then gives you x equals 9. So real quick here, can I accept 9 as an answer? Yeah, I can't accept 3 and negative 3, but I can accept 9. Alright, jumping to the next one here. I think you guys should be able to do this one. Alright, let's see. First is the whole concept of domain. What can domain not be? Anybody? Negative 1 still be okay, right? Because it'd be 2 over negative 1. This would also be negative 1 times negative 1 is a positive 1. So 8 over 1 is just 8. So negative 1 is still okay. 0 is the problem, right? Because 2 over 0. And 0 squared still be a 0. So 8 over 0. That's a problem. So 0 is that problem here. Okay, what's the common denominator? Yeah, if you have a choice between x to the 1, or your variable to the 1 power, that same variable to the second, we always choose the higher power. We always choose the highest power as the common denominator. And all yours to finish it off, if you haven't done so already. Alright, so multiplying through by the common denominator of x squared everywhere. So in the first one, x squared times 1, because there's no fraction to reduce by at all. On the second one, the x's will reduce a little bit here, because that leaves you just an x on top, so negative, don't forget the little minus sign in front, so negative x times 2 is negative 2x, and the x squareds cancel completely, giving you just 8. Hey, I see an x squared, I see an x term, something about setting over to 0 and factoring, is that right? So let's, as soon as you see an x squared somewhere, you know you're going to be factoring. So let's move the 8 over, that becomes a minus 8 on the left hand side. two numbers, multiply to negative 8, add to negative 2. I got 4 and 2. How about, yeah, negative 4, positive 2. I think that'll work. So x minus 4 and then x plus 2. And again, you can do it the quick way if you like, and you can write the answer taking the opposite, or you can separate them out using the zero product principle. If two numbers are multiplying to give you a 0, that means each of them can be set equal to 0, and solve that way. So I got x equals 4, and I also have x equals negative 2. Alright, can I accept both? Can I accept one? Can I accept none? As far as domain restriction, I can accept both of them, right? So therefore the answer is as x is equal to 4 comma negative 1. Most textbooks here will always put them sort of like in increasing order. They'll put the negative 2 first, then the 4. It doesn't matter. As long as you have both answers there and you got them, you're doing good. Okay, number 6 here. Kind of looks weird at first here, but let's see if we can simplify it out. Alright, let's go for it here. Domain restriction is, now we got ourselves a y value instead of x. Y cannot be what? I go with that. 4, negative 4, or negative 4 and 4, whichever way you say, that's fine as long as both answers there. Alright, and then you can cross multiply if you like, but see how the two fractions, but then you got 3. Look at this, you got x plus 1, y plus 1, they get y plus 4, y minus, that's going to be 2. Cross multiplying would probably not be a good idea here, because then you have 3 binomials multiplying themselves together. I'd probably just go with the common denominator. So what is the common denominator? You got a 3, y plus 4, and then a y minus 4. Multiplying the left hand side. Then you got the 3, y plus 4, y minus 4, multiplying the right hand side. Again, looks pretty big at first here, but right after this step, then things become a lot easier. Let's see, 3's are gone. X plus 4 is gone. So really we have x minus 4 multiplying x plus 1. Not x, sorry, y. Y minus 4 times multiplying y plus 1. On the right hand side, y plus 4's are gone, y minus 4's are gone, so really 3 times 8 is 24. Hey, that's kind of cool. Y minus 4, y plus 1 is already in factored form. The only problem is it's not equal to 0, it's equal to 24. So if you guys remember those, what we have to do here, we have to FOIL everything out, move the 24, set finally equal to 0, and then factor here. So let me rewrite the problem here. FOILing everything out, y times y is y squared. Y times 1 is a y minus 4y makes minus 3y. And then negative 4 times 1 is a negative 4. Subtracting the 24 from both sides should give you a 28, now set equal to 0. And then you need two numbers. Multiply to negative 28, add to negative 3. Negative 7 and 4 would perfect. Alright, so if those are my factors, what are my solutions? Perfect, yeah, just take the opposite here. And the previous textbook that I used to use, it always gave these as, these are possible answers. And so what you had to do, sometimes you had to plug it back to the original problem. In this case, we've got to check our domain. So these are possible answers. Is there a number that does not work? Negative 4, that gets crossed out. So really the only true solution here is y is equal to 4. I'm sorry, y equals 7. That's the one that works. That's the one that, as we plug in, we'll still have numbers to work with, and each side of the equation will equal each other. Oof, getting a little sophisticated here, huh? Jamming. Okay. Now let's turn just a little bit to a different concept here. The whole concept of formulas. Let's go down to formulas. So far we've been getting a solution. Here's what we're going to have to do here. So solve for y. So notice it's solved for x. What we want to do is we want to solve it for y. We'll see something like that in chapter 8. We'll look at what the meaning behind this equation is. Alright, if we're trying to solve for y, let's get rid of our fraction. So let's multiply both sides by y minus 1. So minus 1, y minus 1 times the left-hand side, y minus 1 times the right-hand side. Distributing the x to the y. So how about xy? Distributing the x to the minus 1. How about a minus x? Everything for the left hand side of the equation. The right hand side, the y minus 1's cancel each other out. So just y plus 2. Alright, so notice for these problems we're trying to solve for y, but y is on both sides of the equation. So let's do this here. Let's move all the y's together to one side. All the stuff that does not have a y, let's move it to the other side. So in this case, we're going to subtract y from both sides. And you can do this all in one step. I'm going to just sort of show you the two-step process. So notice I got all the y's on one side. So now I got to sort of sweep away all the stuff that does not have a y. What should we do? Yeah, move the x to the side. Let's add x to both sides. And xy minus y is equal to x plus 2. Now we've got ourselves another problem. I'm trying to solve for y, but I have two terms with y in it. Perfect, you got it. Factor out the y. Factor out the y in front. Leftovers would be x minus 1. And we get to divide through by x minus 1. Those would cancel themselves out. That was the whole point of it. Therefore, x plus 2 over x minus 1 is an answer. Alright, and notice that's kind of weird. If you see this, the original problem and the problem itself is the exact same thing except for the variables being changed. That's a very special sort of function. We call it a one-to-one function. We'll see that a little bit later. Again, beginning of chapter 8 is when we figure out the meaning of sort of something like that. Alright, let's try out another little formula here as well. Give you a little bit of time here. Some people are still finishing it up here. Alright, how about this one here? Solve for x. So 1 over a is equal to 1 over x plus 1 over b. Alright, I'm going to start it as well here, try to catch up to you guys here. So hopefully AXB is what you got for the common denominator. Multiplied every single term by AXB. A's are gone for the first term. How about just xb or bx, whichever way you want to write it. X cancels for the other term, leaving it just a times b. And b cancels, leaving it as xa. And we're trying to solve for x. Again, very similar to the previous problem here. Let's move all the terms with x in it to one side. Let's move the ax over. So how about bx minus ax is equal to ab? And just like we did on the last equation that we solved here, let's just factor out the x. So it's b minus a. Everything else remains the same. Now we get to divide by whatever's multiplying x. Alright, dividing through by b minus a, and we get ourselves our final answer of x is equal to a times b over b minus a as our answer. Alright, and then the other section, 2 problems on this as well. So we've got the formulas taken care of. We also have something called the graphing portion of this section. So how do we graph these? We learn how to solve them. We learn how to solve formulas with them. And now let's graph them. And the book was just a little bit too wordy in the way it said it, so I'm going to do the way the book does it, but just a lot more concise here. So first of all, remember the whole domain problem? What's the domain problem here? What causes the domain problem? It's 3, isn't it? 3 is the problem on the bottom, because 3 minus 3 on the bottom is going to be a 0. Then you get 2 over 0. So here's what we do: is we say since x does not equal 3, that's my domain restriction, 3 is going to be our vertical asymptote. Fun new word here. Took me a while to learn how to say that correctly. So vertical asymptote. What does the asymptote mean? I think if you guys had Algebra 2 in high school, you looked at that too. This is a vertical line in which the real graph doesn't touch it. You can get closer and closer and closer to it, but it never touches this line. we'll see it as we graph it. Okay, the second thing we want to do, we can let's do that. Let's graph it already here, just so we have it. So there it is. So the vertical asymptote, we should label it as x equals 3. That's what we say. X equals 3 is my vertical asymptote, and it's a dashed line, which means it's not part of the answer or not part of the graph of the solution yet. Remember, solid lines are the ones that are solutions. So this graph somehow never touches this vertical line. Also, it never crosses a vertical line. It can't just sort of cross through it, because if it crosses through it, it would actually touch somewhere along this line. Okay, next, we're going to figure out just a few more points. Now, remember how I told you, if you don't know what a graph looks like, you can always make a table. So for these guys, you can always make a table. Except sometimes you may just need 3 points, sometimes you may need 17 points. So it's a lot better to sort of get used to what the graph sort of should look like, and then from there you can know. So the main issue with these graphs is this vertical asymptote concept, because we do have a domain problem. Alright, let's do this here. Let's figure out the Y-intercept. Alright, the Y-intercept is where it crosses the y-axis, and notice where it crosses the y-axis, that's when x is equal to 0. So all we really got to do for this function is to figure out what in the world is f of 0. Alright, plugging in a 0 gets you to negative 2 over 3, so how about a negative 2/3? And let's graph it. What would negative 2/3 be on our graph? About right there, is that right? 2/3 of the way from 0 to negative 1? Okay, that's 1 point we got, and technically we only really need 1 more point, and we got it. The X-intercept. Now the X-intercept is a little different. That means when is f of x equal to 0, or when is the y value equal to 0. So we're going to take this f of x value right here and make that a big O 0 right there. So 0 is equal to 2 over x minus 3. Alright, how do we solve this? I think we multiply through by the common denominator, is that right? Multiply through by x minus 3 on both sides. As you multiply this way here, the x minus 3's will cancel. Hey, stuff with that. Is that a true statement, false statement? What do you guys say? False statement does not work. Okay, so that means there's never a time where this guy crosses the X-intercept. So that's weird. Okay, so that means we have a vertical asymptote to deal with. We have a single point that we know of, and then we know it does not cross this line right here. Never, ever, ever, ever. Based upon that, we know what it looks like already. Okay, so these graphs, what they usually look like are like this. They're either going to go like this, or they're going going down like that, and then they start back up and they go like this. That's kind of what we've got to decide, is where is that shift going to happen. So this dot sort of gives it away. If this dot is down here, we know it's never going to cross this line here. So we know that the graph starts a little bit below the line. It starts off a little bit below the line, like somewhere here somewhere. And then we graph it. It has to go to this point here, so it eventually goes to this point here. And then it's going to have to turn because it can't cross this line either. So it's going to turn like this and sort of bend down forever. And there's my little arrow, bending down forever. My little arrow over here. Okay, good there. And the reason why I knew that is because of the vertical asymptote and that little point right there. If the point was above the line, then I knew it would go higher and higher. At the vertical asymptote, there's a break in our graph. So that means it's going to start back up very high over here. And then as I bring it down, it's going to slowly turn, and however you want to sort of go closer and closer to that X-intercept. See it, sort of make sure it sort of is bending so that it looks like it's going to sort of flatten out before it gets this line right here. Okay, let me go back just through a little bit here, just so we got the concept here. So no X-intercepts, we got our graph. Now if you want to, you can always make a little table, no problem. Make a little table, put in some more points, put in a 1 into here. If you put a 1 into here, you're going to get 2 over negative 2, and you're going to get a negative 1. Put a 2 into that. 2 goes into our x, see what our y value is going to be. That's going to be 2 over 2 minus 3, or 2 over negative 1, or negative 2. You can't put a 3 in there, right, because of that whole problem there. So you know it's going to keep on going that way. Then if you start putting a 4 to there, notice what happens here. 4 goes into that. That'll become a 2 over 4 minus 3, or a 1, or just positive 2. Put a 5 into there, it's going to give you a 1. So notice where the dots are. So if you need sort of more points to sort of fill in, just to sort of see how you see the graph, no problem. Then you can sort of fill in a few more points. But the points that are the most important is vertical asymptote. You want to know where the graph is going to split off. And then intercepts, if you got those two concepts there, you're good to go. You should be able to get the graph right from them. Okay, so the other graph has to come down like this and sort of turn. Okay, one more time. This is a practice problem here. Very, very similar. The only thing I changed is I changed it into a +3 instead of -3. Just wanted to be able to see if you guys try this yourself. So all yours. Alright, I'm going to start as well here. So those are trying to do it with me here. Let's go for it here. So again, the whole concept of domain issue is x cannot equal -3. So that is the case. That means I know what my vertical asymptote is right away. My vertical asymptote here is x is equal to -3. Y-intercept, plugging in a 0 for the x value, and if we do that, you get ourselves a 0 plus 3 on the bottom, or 2/3 for that answer, and graphing that. Turn around to do the x-intercept. Y is equal to f of x, which is 0. So the y value is 0 now. Or the f of x value is 0 now, and if that is the case, get x plus 3, multiplying both sides by x plus 3, leaves you with a value that's not true. So therefore no x-intercept. And what I did, I made a little extra table here, but before we even make the table here, let me go back up just a little bit here. Alright, based upon that, would you be able to graph this? And if you can do that without making the extra table, you did really good. So that means there's a break here. It is above the line, doesn't touch the x-intercept, so therefore it has to be coming down this way. You have to come down this way, touch this, and then turn and curve so it doesn't touch the x-intercept. And again, just sort of writing it out. If you went like this, you touch that right there and curve it so it's not touching. Don't curve it back up though. Make sure it's still sort of coming down closer and closer to that line. That means the other side is where it starts low. That means it has to curve this way. Alright, and again, if that was not all that clear, you can always put more points in. You kind of see how that's going to happen. You can put -4 in, -5 in, see those little points there? They turn out to be like this, and eventually you should have a graph that does that. Again, same as the graph that we just had previously. Alright, jumping to the next section, which is the application sections, or word problems here. Alright, I got 4 types. We're going to cover 4 of each type, and then we're going to get into a little bit more sophisticated graphing, like we just did before. So maybe for these, what I decided to do is show you the example from the textbook first, just to sort of get you a mindset ready for it, and then we'll jump into the problem itself. Kind of helped out. So for practice problem number 1, we're going to look at example problem number 1 and see how the book did it. So it says one number is twice another. So notice what they did. They said x is equal to the smaller number. The larger number, they said it equal to 2x. Hey, I think we did something like that, didn't we? Ours was 3 times as big. It says the sum of their reciprocals is 2. So notice the reciprocal of x plus the reciprocal of 2x added together gives you 2. Look at that, multiplying through by common denominator, which is 2x at this point, getting rid of their denominators and eventually solving it out, and you're done. Cool. So label what is x, label the quantity that is defined by x, and go from there. So one number is 3 times another. The sum of their reciprocals is 4/3. X I put as one number. Again, you could put it as the smaller number, the smallest number. You could put it as the first number, whichever way you want to label it. So one number is 3 times another. So that one, the next number has to be the 3x. Alright, it says the sum of the reciprocals is 4/3. Okay, so reciprocal of x would be 1/x plus reciprocal of 3x is 1/3x, and then the result is 4/3. Alright, the only thing we've got to do that the book sort of doesn't talk about as much here is the whole concept of domain. What is the number I will not use, even if I get it? What would cause zeros on the bottom? Hey, a 0, huh? That would be 1/0. This will be 1/0 if it is the case. So off to the side somewhere, just kind of write x cannot equal 0. If I get that answer, I have to discard it. Alright, in this case, what's my common denominator? 3x. Let's go for it. Let's multiply every single term by 3x. So let's see, the x's are gone off the first one, leaves us with 3. 3x, everything cancels off the second one, leaves us just with a 1, and leaves us with 4x. So adding the 4 together, dividing by 4, how about x is equal to 1? That's what allows us. So actually that makes sense, huh? Because if it's 1 over 1, which is 1 plus 1/3 would give you 4/3. One whole piece plus another third would give you 4/3 of a piece. Okay, example 2, starting with that, then we go into practice problem number 2. Alright, almost forgot here. Again, you can't just say x equals 1. That doesn't mean anything with the problem because there's no x's in our original problem. So you have to write off an English sentence that makes sense here. So how about the two numbers are 1 and 3. Alright, good there? Hopefully. Again, we're just going to tackle one of each type here. And we're just going to go kind of quickly here. Jumping to example number 2. This is, I think we talked about it before. Remember, this is the dirt problems, or the distance is equal to rate times time. This time, instead of looking at the distance, we're going to be looking at the time factor. That's kind of what we're doing. So it's going to work a little bit different here. So two families from the same neighborhood plan a ski trip together. The first family is driving a newer vehicle and makes the 455-mile trip at 5 miles per hour faster. Second family is traveling older vehicle and they're going a little slower. It says the second family takes half an hour longer to make the trip. So let's see what we've got. We got this little box idea. Remember the box idea that we had last time for word problems? D is the column header, R for rate, T for time. We know the distance already, so we got the distance is easy. We know that the first family is driving, the rate is 5 miles per hour faster, so it's x plus 5, where the second family is just x. And here's the stuff we don't know. We're missing any time factor here, right? We know rate, we know distance, but we don't know the time at all. And so if we think about it, if rate is equal to, distance is equal to rate times time, we have a relationship between these three. The relationship is this right here. If I divide by that, time is really the fraction of d divided by r. And that's really what goes into this last equation, is d divided by r. It's the distance divided by the time it takes. And then it says that it took them a half an hour longer, so second family. So this family here was a half an hour longer, so that means family 1 plus 30 more minutes gives us family 2. Are we good? Again, just sort of setting it up initially here. So let's go to this here. So a boat can travel 50 miles per hour in still water if it takes the same amount of time in the boat to travel 2 miles downstream as it takes to travel 1 mile upstream. Find the speed of the current. Whew, okay, let's go for it. Okay, so let's go for it here. We've got to define what we're trying to find in the first place. X is the speed of the current. It's how fast the water is moving in the river. And again, if it's an airplane, it's the tailwind or headwind. And so we have this little box, D, R, T. And in terms of rivers, that means we have one something going downstream, the other something going upstream. That's what technically is, especially when you change direction. I mean, downstream the water is flowing with you. The water is actually helping you to go down. Upstream you're fighting the water. All right, let's see if we can put it all together here. So first of all, downstream 2 miles, is that right? Upstream 1 mile, but the rate, what's the rate? If you're going downstream, isn't it how fast the boat is, and then the speed of the current is helping you to go down even faster? To go, and so what's the ratio? Ratio is d over r, so it's the distance divided by rate should give you that t value at the end. So that's the time for the downstream. Alright, upstream is 1 mile, and now the current is going against you, so it's 15 minus x, and so the equation you want is 1 over 15 minus x. Okay, now there's going to be some kind of relationship between these two numbers. Either it took the boat, like I said, half an hour later. It maybe the total trip took 4 hours, and if you're saying the total trip took 4 hours, you're going to add this together to give you a 4. But in this case, it says the same time, same amount of time. So because it says same amount of time, we're going to set each of these guys equal to each other. Alright, I'm going to go a little faster here due to time here. So domain restriction again, it can't be a 15 or a negative 15. And this time I think it's cool to cross multiply. There's no issues here. Let's cross multiply. So 2 times 15 is 30. Minus x is a minus 2x. 15 plus x times 1 is just going to be that 15 plus x. Alright, and solving that problem. Let me rewrite it over here. So minus 15 for both sides gives you 15 minus 2x equal to x. Let's add 2x to both sides. How about if 15 equals 3x, and how about x equals 5? And the question is, can I accept that as an answer? That is good. Okay, here we go. Can you write an English sentence identifying what is your variable and include the number and include the units? So in this case, x, remember, there's the speed of the current, so that means the speed of the current is 5, and then we're in terms of miles per hour, so it'd be miles per hour. Okay, so this is one type of distance problem, and what we say type is because it says in the same amount of time. So when you got to the last column, what you do is you put the two answers together. But another type of distance problem is when you know the total. Let me jump to it here. You know the total time it took. So a very similar setup. The equation is going to be changed just a little bit here. Alright, and I'm going to get started here so we can finish on time here. So in this case, we're trying to figure out the speed of the boat. So identify our variable. X is the speed of the boat this time. The current of the river is moving at 2 miles an hour, downstream of course. And then we figured out when we took off and we figured out when we came. But we forgot to check our time when we turned around. But we're interested in just the whole concept of speed. How fast were we traveling? So column setup. DRT. We have upstream, downstream, whichever way you want to write it. I just put down the I put the upstream on top this time. Alright, so the current is 2 miles an hour. It takes the boat a total of 3 hours to travel 8 miles upstream, so 8, so if the current is 2 miles an hour, to go upstream we're traveling at x minus 2. However fast the boat is, current is pushing us back at 2 miles an hour. The distance that we travel is 8, and again this is the total time. Total time to do everything was 3 hours, so that's not going to come in yet. And the return trip, and this time since we're going downstream the current was actually helping us, so we're at x plus 2 this time. So can you write your ratios for the last column? What's your ratios? Alright, how about the first one, 8 over x minus 2. The second one's 8 over x plus 2. And then we go back, and this one's the total hours. We know it took 3 hours to do everything. So that means we're going to be adding the first, the time it took to go upstream, the time it took to go downstream is added to give you a 3. Alright, going a little faster here so we can finish up. This one's just a long one to finish, that's all. Alright, first of all, what two numbers can we not use? Yeah, 2 and negative 2 would be problem areas for us. But in fact, because this is a word problem, also any kind of negative would be a problem as well, right? Alright, so let's see, let's say 2 and negative 2 can't work here for us. We multiply through by the common denominator, which is x minus 2, x plus 2. So x minus 2's cancel, so I'm multiplying 8 times x plus 2. On the second term, the x plus 2's cancel, 8 times x minus 2. This one, nothing cancels. And if I multiply x minus 2 times x plus 2, remember there's a difference of 2 squares, so how about x squared minus 4? Alright, distributing the 8 and the 3 here. And simplifying as much as we can. Now I have to solve this, and I notice again, here it is, I notice a x squared term here. If I'm going too fast, or if you need to see the slides later, no problem. Give it to you later. Here, let me rewrite this here. So I can move the 3x squared and the 12 over, or I can just move the 16x. I think I just want to move the 16x over. So set equal to 0, and now I need to guess and check. The only way I can get a 3x squared is 3x times x. So I need two numbers multiplied to give you a negative 12, and then when we do the middles, they'll give you a negative 16. Again, since we're running low on time, I'm going to give them to you. It should be a negative 3 and negative 4. Is that true? No, I'm just guessing here. What am I guessing here? Let's see. Will that give you that middle that we want? That's a negative 12. No, that's a negative 15, huh? Oh, that's not a negative 16. Okay, so let me jump here. How about this? See if this makes sense. Will that make sense? Next, the negative 12 at the end. So this is a negative 18 plus 2. Would that make negative 16? Yep, that would work. Set each of them equal to 0. So negative 2/3 for one of them and 6 for the next one. Remember, for our domain restriction, we can't use -2 or a +2, is that right? But even further, because this is a word problem here, can the speed of the boat be going negative 2/3? Nah. So this one right here also goes away just because you can't have really negatives for speed. So the answer is 6, and then again, can you write as an English sentence telling me what the variable is and then giving me units. Example 4, as when we start here, example 4, it talks about a pipe putting water into the pool, taking water out of the pool, and how does that work. And it's almost like the dirt problems that we did. Distance is equal to rate times time, but we call it work problems. And so example 4 and problem number 4, and in fact, are the exact same thing. So I want to guys at least give you guys a visual here. So you have a inlet pipe that's pushing water into the pool, and we know from the size of the pipe and all that good stuff here that it can actually fill this pool in 10 hours. At the same time, we have a little drain right over here, and the drain, if we open it up, it can actually empty the pool in 12 hours. So what happens if someone is trying to put water into the pool at in 10 hours supposedly, and they left the drain open? That's our question. So how much time will actually take to fill the pool then? So as we did before, we're going to make a little box like this. Again, just like the dirt problems, except now we're going to use the W for work. Work is equal to rate times time. And so the amount of work a person does, again, same thing as distance and driving. It's how fast you can do it in, and then how long of the time are you doing it. So we think of probably like typing. Typing is this type of work, and if you say I can type 20 words per minute, and you do that for 4 minutes, you should have about 80 words. So same exact concept as dirt. Okay, so we got the inlet pipe, and we have the drain. Alright, so 10 hours here. If that is the case, what we're going to do is we're going to take this rate, but this rate is not going to be in 10, it's going to be a fraction. So how much of the work can the pipe do in a single hour? That's our question. And so if it takes 10 hours, it actually does 1/10 of the work in a single hour. Then the drain is happening at 12 hours. So again, if it takes 12 hours in a single hour, how much of the work will be done? 1/12 of the work would be done. Okay, for time, we're going to put X, because they were both open at the same time, or both working at the same time. It didn't take another one to start a little later. For these work problems, what we do is we multiply straight across into this W column. So X times 1/10 would be X over 10. X times 1/12 is X over 12. And we're going to set up an equation here. This is the equation. The equation is the inlet, the work that the inlet is doing. Now this could be plus or minus, because the drain is actually draining the water out. They're sort of doing a work against each other. We're going to put a minus here. Minus of X over 12 equal to, and this is another weird thing, it's 1, because we have one single pool that we're working with. If the drain pipe went to 4 different pools, this would be a 4. Alright, so notice nothing, no domain restriction here, because we only have constants on the bottom, so we've got to multiply through by the common denominator, a number that 10 will go into and 12 will go into. It's going to be 60. So let's multiply everything through by 60, which makes 6x minus 5x is equal to 60. In this case, kind of funny how the numbers worked out, because the common denominator actually becomes the answer. Not always that happens. And so we have x equals 60. So our variable was in terms of hours, so in order to fill the pool, it will take 60 hours because that drain pipe is, in a sense, leaking the water out. Okay, and let's go one more problem here, something with the graphing. So this is a little bit more complicated than we did in the last section. We're going to try to graph these here. So y is equal to x minus 3 over x minus 1. And I'm going to take a little bit of a different order. The book sort of does this in this order, so I might as well do the same thing here. So x, the y-intercept. Hopefully remember that still. How do you get the y-intercept? You plug a 0 in for the x. And if you plug a 0 in x over here and here, you get yourself a negative 3 over negative 1, or just simply 3. So I got my first point. I got that one. Step 2 in the process is the book wants you to find the x-intercept. In this case, you just do the other way here. You put a 0 in for the y value. And again, did this before in the previous section. Except this time we are going to actually get an x-intercept here. So as you multiply both sides by x minus 1, on the left everything cancels, but on the right hand side there's still that little x minus 3. So if we add 3 to both sides, you have an x equals 3. There's my x-intercept. Cool. So I got a y-intercept of 3, x-intercept of 3. Number 3 is something we talked about, the vertical asymptote idea. And remember, the vertical asymptote is when you look at this here, it's when this will give you a 0. And what gives you a 0 is a 1. So x equals 1 is the vertical asymptote. Again, that's going to be a hashed line or a dashed line coming straight down. Alright, the new stuff here that we haven't talked about is something called the horizontal asymptote. Now the horizontal asymptote is a little bit tricky. Let me give you the idea and the concept of it, and then we'll sort of look at the shortcut way of finding it here. The horizontal asymptote is what happens when numbers become very, 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 very huge. So in this case, let's say we went out to 1,000,000. Let's say x becomes 1,000,000. So 1,000,000 over here and 1,000,000 over here. So 1,000,000 subtract 3. Ooh, that's going to be 999,997. Well, over here it's going to be 1,000,000 subtract 1 is 999,999. And the question is, what is this number sort of close to? Well, it's almost like the same number, right? The little extra subtract 3, the little extra subtract 1 didn't really affect the problem that much. So notice this is really, really close to 1. So we have y equals to 1. Notice the y value now, as opposed to the x. Now let me give you just a kind of a little different idea here. Let's say this problem, I'm going to change the problem just up just a little bit. What happens if the problem was 2x minus 3? Notice if I were to plug in 1,000,000 into here, this would be 1,000,000 times 2 is 2,000,000. Subtract 3 would give you 1,999,997. And 1,000,000 blocked into that, no change for the bottom, that would be 999,999. So notice real quick here, is there a little difference there? Yeah, besides sort of the end number here, isn't this number here really twice what this number is on the bottom. And so how do we find the horizontal asymptote very, very quickly? Let me erase all this first. We find it by looking at the ratio of the leading terms right here. So notice this is 1x divided by 1x, and 1 divided by 1 is just a 1. If I did it over here, 2x divided by x, that would give you a 2. So in this case, you would write y equals 2 for that one. Alright, so let's go on with our problem here. So y equals 1. Alright, so here's what we got. We got 0, 3 as a point along this line. We got 3, 0 as the y-intercept. So I know those 2 points for sure. I got a horizontal asymptote, a vertical asymptote at 1. So I got this guy coming down like this at x equals 1. And now I have a horizontal asymptote coming out at 1. So now the question is, based upon the dots and the asymptotes, how is this drawn? So you kind of have one of two choices here. Let me illustrate that on the next slide here. You can either have the graph going up here and down, or you could say it was down in this corner and then it was up at this corner here. So let me just sort of, so you can see it here. Here's your two options here. There's my asymptotes. So it could be that the graph started a little bit above the horizontal asymptote and shot up, and then it started low and sort of came crossed the x-axis around here, and then came up to the horizontal asymptote but did not touch. Could be that it started low in the lower corner and then finished off in the upper right hand corner. And if you're looking at these here, which one makes sense really now of the intercepts at this point? Well, remember the intercepts are right here. The intercept is at 0, 3 and 3, 0. So even though the graph is not precisely on those points here, but notice it would not make sense for this graph here. So then the final answer, including the points here, would be, there's that 3, 0, 0, 3. So then it would have to be this graph here that starts off a little bit higher than the horizontal asymptote, goes up higher, starts out low, the bottom right hand corner crosses the x-intercept at 3, and slowly moves up to the horizontal asymptote and stops there. All right, that would be the end of 5.6. Thanks, y'all. Okay, let me eat just real quickly and I'll help whoever needs help. Anybody allergic to peanut butter, just to make sure? We're okay? Okay. I can eat my peanut butter and apple.
Have you tried almond butter?
Yes, love that.
Better.
Yes. If there was a choice in the house, that's what I would take. Then we got raw almond butter from Trader Joe's.
Yeah, I have that one too.
Love
I did it with celery.
I took the apple instead of celery, but yes.
I love Trader Joe's.
We live close to the one on Willow Avenue. Willow and Herndon.
Oh, okay, you live in Fresno.
Mhm.